This video promotes radiation safety. One protocol is used to demonstrate the safety principles that apply to the use of radioisotopes in the modern biology laboratory. It is intended to supplement the formal instruction provided in each institution and each laboratory. This video is not a substitute for a safety training program.
Respect is something that you really want to gain for this material. It's certainly something you wouldn't want to carry out of the laboratory you're working in and expose other people to. The thing to keep in mind really is that you can contain it. And if you're practicing safe techniques, you're going to have less of a chance of contaminating yourself or a piece of equipment.
Laura Brown is preparing to do random primer labeling for southern hybridization. By surveying the work area, Laura assures herself that there is no residual contamination from past operations. The most common radionuclides in the modern biology laboratory vary in the types of emission and their associated hazards. Phosphorus-32 emits energetic beta particles that can travel up to 20 feet in air. Aside from ingestion, its principal hazard is exposure to skin and eyes. A minimum of 1/4 inch of plexiglass provides effective shielding. The beta emission of sulfur-35 and phosphorus-33 is low energy. Since ingestion is the principal hazard, no shielding is necessary. The tritium betas have such low energy they are not detectable by the Geiger-Müller counter. Ingestion is the only hazard. Iodine-125 is a gamma and X-ray emitter. In its unbound form, it presents an inhalation hazard as well as a source for whole-body exposure, for which exposure limits are significantly lower than for the skin. A fume hood and leaded acrylic or lead shielding provide effective protection. When the package of P32 was first received, it was checked for contamination. How much radiation is this vial giving off? How much risk does Laura incur? The vial contains 1 millicurie of P32. Uncapped, the stock vial emits 200 millirems per minute of beta radiation. She uses 50 microcuries in the protocol. The amount of radiation which Laura receives to her hands during her work on this protocol, approximately 15 minutes, will be less than 5 millirems, or 1/100th of 1% of the permissible annual extremity dosage. Laura's defenses are time, distance, and shielding. The goal is to keep exposure, ALARA, as low as reasonably achievable. It's important to use the correct radiation detector. Beta emission is detected by the Geiger-Müller counter. The more sensitive pancake-style detector should always be used when working with low-emission isotopes like S35 and P33. The scintillation probe detects the low-energy Bremsstrahlung radiation emitted from the stock vial. Plexiglass provides no shielding for these emissions, but the radiation being measured is insignificant. The isotope should be completely thawed to avoid splattering while pipetting. The dosages shown represent the radiation level at that site. Note the effect of shielding. Laura uses aerosol-resistant pipette tips to avoid contaminating the pipette membrane. Here, a lower dose to Laura's hand could be easily achieved by using a plexiglass holder for the Eppendorf tube. Laura's mindful of what materials come in contact with radioactivity and how they need to be disposed of.
You need to distinguish when you're working with hot material and when you're not working with hot material. You need to discard waste that's not hot into a regular waste container.
The use of screw-top Eppendorf tubes prevents popping during heating and provides containment during centrifugation. The end window Geiger counter indicates the amount of activity. Frequent checks of gloves and equipment alert Laura to contamination before it can be spread further. And she doesn't forget to check the centrifuge. Since exposure time is a factor in the worker's dosage, it matters how efficiently a procedure is performed. Laura always posts a copy of the protocol for reference. Keeping an inventory of radioactive stock and waste is required at all institutions. Laura next injects the incubated target solution into the spin column. The Geiger counter here is used to indicate the presence of the isotope.
If you double glove, then you have the added advantage that if you should contaminate your hand, you can take off that outer layer of gloves and still be protected inside. And you'll have time to put on another pair of gloves without worrying about contaminating your skin.
After spinning the column, Laura uses a hemostat to retrieve the Eppendorf tube. Forceps or tongs might slip, causing a spill. Laura now prepares to add the radioactive target solution to the hybridization filter.
There can be an orientation in the beginning, and you hear about how to work with it, and then someone can show you how to work with it. But it's really when you have your hands on it that you pick up all the little techniques that are important in handling radioactivity safely.
Using a bag considerably larger than the filter provides a container for the air bubbles and prevents the radioactive solution from escaping onto the bench. Submerging a secondary container in the water bath assures that any leaks will be contained. A thorough post-procedure survey confirms that no contamination has occurred.
If you're monitoring, you're going to pick up that contamination and you're going to clean it. And therefore, as you're walking out of the laboratory, you won't be exposing other people.
Of course, hand washing is a must after completing any procedure. The waste from the washes should be disposed of according to the policy of the local institution. Collected waste must be stored in a liquid radioactive container. A record of the amount of waste disposal must be maintained. After the filter is prepared for autoradiography, Laura monitors the cassette for contamination. Other protocols, like cell labeling and iodination, require higher levels of radioactivity. Extra care should be taken with shielding to keep exposure as low as reasonably achievable. At millicurie quantities of P32, wearing a ring badge is required at Randy's institution. The hand that holds containers most often is the one that should be monitored. Iodination requires lead shielding and also presents an inhalation risk when the unbound form is used. Working in a fume hood or a glove box exhausted through a charcoal filter will contain iodine vapors. Whenever working with radiation, keep yourself safe by observing these principles. Know your isotopes. As low as reasonably achievable. Remember time-distance shielding reduced dose. Use personal protective equipment. Perform correct monitoring. Good equipment and good laboratory practices can keep radiation hazards small. Yet even that small risk can be eliminated in some instances by using alternative protocols, such as the chemiluminescent technique in place of random primer labeling. Think about it.